Hello, and this time we're going to look at a couple of examples of applying this technique of using phasors to analyze AC circuits to dividers, a potential divider and a current divider. We'll start off with this problem, which is a potential divider. We have the phasor representation of the voltage source here, and then two components which have complex impedances arranged in the classic divider format. So we can just apply the potential divider equation. The output, 4.7 millivolts in this case, at a phase angle of 90 degrees, is equal to the input, 4 millivolts at 90 degrees also, divided by the total impedance in the circuit, which would be j omega L plus 1 over j omega C, and multiplied by the impedance over which the voltage is being measured, which in this case is the inductor, so that's j omega L. We know the value of the inductor, we know the value of the capacitor. What we don't know in this case is the frequency omega. So we have to do a bit of algebra. Now the first thing I note, looking at this, is that at 90 degrees on this side, and this at 90 degrees on this side, cancel out. Because 4.7 millivolts at 90 degrees could be written 4.7 millivolts times e to the power of j pi over 2. And this 4 millivolts at 90 degrees could be written 4 milli times e to the power of j pi over 2. That is the polar representation of this complex number. So these two just cancel out. The millis cancel out as well. Could just write 4.7 on this side equals 4 times j omega L over j omega L plus 1 over j omega C. Next thing I'm going to do is multiply up by j omega L plus 1 over j omega C. That would give me 4.7 j omega L plus 4.7 over j omega C equals 4 times j omega L, and then multiply up by j omega C. Well, j omega L times j omega C, that would give me j omega L times j omega C, which is j squared omega squared LC. J squared is minus 1, so that's minus omega squared LC. So I would end up here with minus 4.7 omega squared LC plus 4.7 equals 4 times minus omega squared LC again. If I bring this term here over to this side of the equation, that would give me 4.7 equals 4.7 minus 4, extracting the common factor of omega squared LC, and therefore that omega squared is 4.7 divided by 4.7 minus 4 times LC. And from here on in, I just need a calculator in order to calculate what the square root of 4.7 divided by 4.7 minus 4 times L, in this case 1, times C, in this case 68 picofarads, actually is. And the result, omega is 3.142 times 10 to the power of 5 radians per second. And you could leave it like that, but most people, when they quote frequencies, quote the frequencies in terms of hertz. So if I took this result, 3.142 exponent 5, divided it by 2 times pi, I would convert it to a frequency in hertz, and the answer would be 5 times 10 to the power of 4 otherwise known as 50 kilohertz. So the answer, this circuit must be going at 50 kilohertz. Now I chose this example in particular because you might have noticed something quite interesting about this potential divider. And that is that its output voltage is bigger than its input voltage. The voltage across the inductor, 4.7 millivolts, is larger than the voltage at the top of the potential divider, which is only 4 millivolts. And this is something that cannot happen at DC with just resistors. But when you've got capacitors and inductors in the circuit, you can get this to happen, because what's happening here is that this j omega L and this 1 over j omega C, which is actually equal to minus j over omega C, that's a positive imaginary number, that's a negative imaginary number. They are, to some extent, cancelling each other out, and you end up with quite a small denominator in this expression. And you can get quite large voltages out of potential divider circuits like this. The second example I'll do is of a current divider. Now here we're given the total current flowing out of this node, and that current is being divided between the current flowing through this inductor and the current flowing through this resistor. Once again, the question is, what is the frequency? And I would proceed as follows. Firstly, if the current flowing down this way is 2.5 nano at 90 degrees, then the current flowing up in the other direction must be 2.5 nano at minus 90 degrees. Since 2.5 nano at 90 degrees would be there in the Argand diagram, multiply that by minus 1, it would end up down here. That is 2.5 nano at minus 90 degrees. So the phasor representation of the current flowing up through this current source is 2.5 nano at minus 90 degrees. In other words, it looks like a sine wave. The current that flows through the resistor I can get from the current divider equation. That's just the total current multiplied by the other impedance, which in this case is j omega L, divided by the total impedance in the circuit, in this case R plus j omega L. And I know what that is. I know that's 1.237 nanoamps at a phase angle of minus 29.7 degrees. Okay, so I can proceed as follows. 2.5 nano at minus 90 degrees times j omega L equals 1.237 nano at minus 29.7 degrees multiplied by R plus j omega L. Let's divide both sides of this equation by this quantity here. That would give me 1.237 nanoamps at minus 29.7 degrees over here, and it would cancel out over there, and I would end up with this. I can work out what this expression equals to using my friendly calculator. 2.5 nano at minus 90 degrees divided by 1.237 nano at minus 29.7 degrees. Didn't really need to type in the nanos, they cancel out, but the result is... Ooh, I missed the 3. 2.021 at minus 60 degrees. So 2.021 at minus 60 degrees times j omega L equals R plus j omega L. Right, if I bring this j omega L over onto this side and take out the common factor of j omega L, I would end up with 2.021 at minus 60 degrees minus 1 times j omega L equals R, and therefore that omega equals R over j times L times 2.021 at minus 60 degrees minus 1. to my friendly calculator. R, the resistor, 150, divided by J times L, 680 microhenries, times 2.021 at minus 60 degrees minus 1. And the result is real, which is a relief. Since if this had been an imaginary or complex number, I would have been very worried because it's supposed to be a frequency. So omega 1.260 times 10 to the power of 5. And once again, if I wanted to write that in hertz, I just need to divide it by 2 pi. And the result is around about, well, actually very close to 20 kilohertz. So I would probably write my answer to this problem as 20 kilohertz. That's all for this time. Next time, we'll have a look at how to use equivalent networks with AC circuits.